Hello, this is the fifth session on strength of material interview preparation. So let's talk about the moment of inertia. So as we see that inertia is nothing but it's a property of a matter by which it continues to resist the state of its rest or motion unless it is changed by the external forces. Okay, that is, it is a resistance from its state of being, that is called inertia. And what is moment of inertia? It is basically quantity expressing the body's tendency to resist rotational motion. It is the inertia of rotating bodies. So inertia is nothing but m times r square. Okay, so in moment of inertia there are two types, mass and the what is the difference between the mass and moment of inertia? Mass is basically, it's a measure of inertia of the body, and it is a unique value. It doesn't depend upon the orientation. But moment of inertia, it is a measure of inertia of rotating body, and it depends on the location and position. That means orientation. It depends on how you put the body and how it rotates along the axis of rotation. Okay. So in moment of inertia there are two types: area moment of inertia and mass moment of inertia. So area is nothing but it's in a 2D and this is in 3D. So the I is equal to AR square, I is equal to MR square. Okay, and it depends upon the body type, body area, how it's the rotation is applied. Okay. So next is the polar moment of inertia, which the symbol is J, and it's a unique value. So to find the moment of inertia, so we can calculate the moment of inertia as along the directions. For this one, it is I is equal to d cube dv cube by h, and for this I is equal to bd cube by 12. So this is moment of inertia, and basically it's asked for when they ask for like what is the moment of inertia, we need to ask that what ask about the axis of rotation. So for multiple axis of rotation we have multiple values, but for polar moment of inertia there is only one value, and because the axis is perpendicular to the plane of the body, so it goes through the center of gravity and has only single value. And this one, most of the time it goes to the centroid, or it can be in the edge also. It depends upon the orientation. So the next one is the radius of gyration. Radius of gyration is nothing but the imaginary radius from the axis to the mass. So for example, this is the distributed mass of in a given random body, and this is the point mass. So what is the inertia, moment of inertia of this point mass? This will be m times k square, and k is the radius of gyration, which is equal to this expression. Okay. So next let's go to the important topic about shear force diagram as well as the bending moment diagram. So for given body such as this, as a cantilever, if you have some force applied, shear force is applied, so this kind of shear force diagram will happen because the shear force is equal in the whole body. So this is the rectangular shear force diagram, but for the bending moment diagram it will be triangle shape. So these are the relations which you will see in later picture. So but the stress is equal to moment by moment, mass by moment of inertia times the length. We will see this later. But the thing is that why we need the BDM? We need BDM because we need to know about the bending stress, which is the normal stress, tensile or the compressive stress. We need bending stress, that's why we also need the bending moment in the body through this diagram. And when we get this bending stress, we will be able to know and check whether the material will passes through the failure point or not, and so that we can prevent the failure. Okay. So next go to how to know from the SFD and BMD about the loading diagram. So if we have if a situation is given something like this, if a loading diagram is given, and we can easily identify what kind of loading is that. So if the moment in the both sides are zero, it is zero here and it's not zero, we can see that it's a point loading at the end, and it's in the cantilever. And if you have a situation like this where the both are not zero, then it's a case of a point loading and with the fixed beams, fixed support beams. And in this case where both are zero, it means that it can be a overhanging beam like this. This is the situation. And also this is another case where both moment of zero, but this one is a centrally applied simple supported beam with the center point load. There are various cases like this, load types diagrams for SFD and BDM. So point load, it is the rectangular, and for here it's triangle. For uniformly distributed load, the SFD is triangle, and here it's parabolic. For uniformly variable load, it is parabolic, and here it is cubic. For moment diagram, one just moment is applied, the SFD is just a line, and the BDM is in a rectangle. You will see these pictures later. So when the slope of the BDM at a point, the slope of the BDM at a point gives the shear force at that point, at that only that point. So the slope, for example, this is the BDM, and at the slope, if at this point the slope is something, this the slope of this point gives the shear force at the particular point. For example, this is the BDM, so the slope is tan theta, and 10 by 10 is 1. That means the shear force at point A is 1. Okay. Second thing is the area of the SFD gives the bending moment at that section. So this is SFD. So this area basically gives the moment at that session. Okay, so this we have to remember it. And then there are different cases. For example, this is the point load. So this is the SFT and the BDM, and this is the moment where it's applied. You can see just the SFT is line here, but the moment is rectangle, and here you can see it is a double bar here. So what we have to observe is that whenever there is a sudden jump in SFT, that means the point load is applied, different points applied, and in BDM the moments are, as you can see, there is a sudden jump here, that means there is a moment here, applied here. Okay. So another thing is that the slope of the moment is equal to the shear stress. The slope of the BDM is the shear stress, and the slope of the SFT is the loading intensity. So as you can see, this is a BDM. For this we have SFT, but when we go to the uniform, we have such a SFT. That means we have a uniform slope. The slope is same. That means the intensity, load intensity is same. That means it is a uniform distributed load. But if you see how such a curve like this, it means the slope is increasing. That means the intensity is increasing. That means it is a uniform variable load. And here you can see the slope is decreasing here from the picture you can see. That means the slope is decreasing. That means load intensity is decreasing, and this is also an example of the uniformly variable loads. Okay. Next one is the picture for such a situation where in the center we have a moment, and these are two reaction forces. But to keep this body in equilibrium, this reaction force is induced, which is equal to the RB. And for such cases, the shear force diagram will be rectangular, but the BDM will be like this, because at this point, wherever the moment is applied at the center, there will be a change in momentum. Okay, and this point the momentum will also be maximum. So let's go to the next example. So the point at which we have the slope of the BDM is equal to fx, and if the slope is 0, then at that point the mx is maximum. Okay, if the slope is 0, at that point we have the maximum moment. That means the fx is equal to 0, and that means the bending moment at that point is maximum. So that we have to identify such point. Okay, and we have to find such points, because at that point we have maximum bending moment. But there are also cases where the bending moment is maximum, but the shear force is not 0, and the slope is also not 0. So in that case also we will have maximum moment. From the maximum moment we can also find the bending stress, because at that point the bending stress is high and we don't want any failure at that point. Okay, there are two cases. The first case is here. For example, we have such a uniform load, and at this point we have SFD shear force is equal to 0, but at the same point we have the maximum moment. That means this point has maximum bending stress. But in another case where the shear force is not 0 and moment is also not 0, for in this case, and the center load is applied, at this point the shear force is not 0, and this point the maximum slope is also not 0. So at this point we have a maximum moment. That means at this point we have maximum bending stress. Okay, and then what is point of contraflexure? Point of contraflexure means the point where the BDM changes its sign from sagging to hogging. So as you can see, this is also a point of, because the slope is increasing and decreasing. This is also a point of contraflexure. But also there is another case, the point on BDM where the slope is 0. At this point also it's a point of contraflexure. At this point the bar actually bends, and so we won't know this point, because as you can see this is a uniform loaded beam. At this point the force is something like this. As you can see here, actually there's a load also applied here, there's a support here also. Okay, So this is bending like this. And this, if you see this BDM for this diagram, it will be something like this. So at these 2 points, the moment is 0. So these 2 points are basically the point of contraflexure. Point of contraflexure means where the BDM changes its sign, that means from sagging to hogging. So that kind of point is called point of contraflexure. So what is the purpose of finding the contraflexure? Because it helps us to know where to apply the reinforcement. Okay. So because the point of contraflexure, what happens is that this is the point of contraflexure. So here there's a tensile stress, and here compressive and here tensile stress. So at this point we want to apply reinforcement so that the failure won't happen. That's why we want to know the point of contraflexure. So there are different cases. So this one is the continuous loaded beam in which we have 2 points, and here this is the overhanging beam. We have only 1 point, and this is a fixed support. We have 2 points here, and the other case is the internal hinge. So the number of contraflexure point is equal to number of internal hinge used here. Okay. So next question is, what is pure bending? Give some example. So pure bending is a case where the shear force is 0 and only bending moment is applied there. For example, is this one cantilever beam which only moment is applied. In that shear force is 0, but the bending moment is only applied. But there are other cases also. In this case, we can see in the center, in the shear force, the shear force is only 0 in this section. That means it's also a pure bending case, but only for this section. Okay. Thank you.